All right, here we are. Well, I guess everything worked out okay at the school. Apparently the power is back on, which is great. I don't know what happened, but this way, at least, we definitely we're able to have a class. And anyone who can't be here, of course, can watch the recording. So what we're going to do today is wrap up the review that we were doing the other day. There's just a handful of trig questions left, and then we can go back and revisit matrix algebra, which we were doing just before the break. Okay, so we have a lot to do today. So we're going to start by opening up that set of review questions, or is it the sample midterm? And the other day we stopped at problem 13, it looks like. So what I've done here too is I've opened up two documents that we've seen before. One of them is that graph of the reference angles and how they're calculated in each of the different quadrants. The other one is that unit circle that enables us to directly look up sines and cosines for many different angles. Okay, so let me show you what I'm referring to here. The trigs, the unit circle graph is this one. And if you remember, the way this works is that you've got all these different angles on here, both in degrees and in radians. But the important thing is that for each of these, the x coordinate is the cosine of that angle, and the y coordinate is the sine of that angle. Don't get that backwards, okay? So that's how we use this. You can instead just use your calculator. We have been using the TI-84 to come up with our trig results. And we also have the questions about reference angles. We have another graph here somewhere, which, God, I've got so much stuff open here. Where's that thing? Here it is. Okay, so this tells you, depending on what quadrant you're in, how to calculate the reference angle. And I do want to point out that this can be used for both degrees and for radians. If you remember the identity, pi radians equals 180 degrees. So I can go through this chart and replace the degrees with the corresponding number of radians. Oops, that's not what I meant to do. Oh, yes, it is. That's fine. So remember, like here, for example, 180, I'm replacing it with pi. This is now pi. And then down here, this becomes 2 pi. Okay, so that's all you have to do to use this exact same chart with radians. Okay, all right, good. So let us go back to the questions. So we're going to start with number 13. And here it is right in front of us. So we're going to start right off the bat with reference angles. Now, we start with negative 120 degrees. Now, if you remember, the way this works is that we go around through the axes in a clockwise direction. Whatever angle we end up with is considered to be negative, okay? If we go counterclockwise, then the angle is instead positive. So negative 120 means that what we're actually doing here is that we're starting on the horizontal axis. We're going 90 degrees to the first quadrant, and then another 30 degrees into the second quadrant. And that's where we come up with negative 120. Now, the important detail here, when it comes to reference angles, really the only thing that is important is what quadrant are we in when we reach the terminal side. If you don't feel comfortable with negative angles, what you can do instead is convert this into a positive angle by noting that you're going 90 degrees through the first quadrant, 90 through the second, and then 60 more degrees into the third quadrant. So the positive angle here is 240. These both mean the same thing. Now, if you look at the way the formulas are written in this chart, I think you'll find it's easier to use the positive angle. So in other words, we're in the third quadrant, which means that the formula we need is angle minus 180. So that means in this case, that would be 60 degrees. Okay. Now, I would also like to remind you what exactly the reference angle refers to. If we find ourselves on this terminal side, what it's really asking you to do is figure out the quickest way to get back to the horizontal axis. So in other words, if I had to, let's say my goal was I'm driving and I wanted to go to the horizontal axis, but I went too far and I ended up down here. How do I get back to the horizontal axis? Well, that requires me to move 60 degrees. So that is what we mean by the reference angle. How far, what is the closest distance to the horizontal axis? Okay, so anyway, now B is also interesting for a different reason. If you notice, it's more than 360. What does that tell us? It means that we've gone around the entire circle more than once, and then another 45 degrees on top of that, because the entire circle has 360 degrees. So it's like you went around, let's say you're lost. You went around the entire circle and then you realize, oh, I know where I want to be, right here. So you went 360 plus 45, and that gives us 405. So we don't need to deal with the 405. The 405 is a very large number. What we normally do is we reduce it to the actual number of degrees that you've traveled into the first quadrant. So we would say that 405 and 45 are actually the same angle. But as far as reference angle goes, it's probably simpler to use the 45 degrees in our formula, which in the first quadrant, interestingly enough, the reference angle is just whatever angle you have. Okay, so in the first quadrant, the formula is reference angle equals angle, which is 45. Okay, so yeah, I mean, you could make the case that it's also 405, but normally you would refer to it as 45. Okay, because what we're really after is how far into the first quadrant did. All right, now you've got the same setup with part C. In fact, this one is larger than 720, which is 2 full circles. So this one needs to really cut loss. I guess you could think of it as going around the circle twice, looking for some address or other. So we went around not just once, but 2 times. Okay, and you can tell because this number is greater than 720. How far? Yeah, 760 minus 720. 40 degrees. So you have to visualize that you went around the circle twice and then another 40 degrees into the first quadrant. And so we just saw before that in the first quadrant, the reference angle is the actual angle that you have, which means 40 degrees. Okay. And then finally, D, we're looking at negative 180 degrees. So again, another negative angle. So negative means we're going this way. But the positive version of that would mean we've come this way. And in fact, it's the same distance. So in other words, negative 180 degrees actually equals positive 180 degrees. Now, how does that help us find the reference angle? We're actually sitting on the border between the second and third quadrants. It turns out that we can use either formula then. So for the second quadrant, we have, 180 minus angle. Okay. Now, by the way, if you wanted to stick with the negative angle, you would get 360, but remember 360 and 0 means the same thing. Then if you tried the formula for the third quadrant, you would also get the same result. In the third quadrant, the formula is listed as angle minus 180. Sorry, I didn't see that question. I don't know what. Oh, you just want to make sure I know you're here. Yes, that's fine. Yeah, no, whenever there's a Zoom session, when I'm done, it'll print out for me a roster of the people who are attending. So, I mean, I don't have to specifically notice that you're here because it'll give me a list after we're done. Okay. All right. Anyway, so the third quadrant formula is Now I lost it. Oh, yes, angle minus 180. It's the same thing. 180 minus 180 is 0. If you insist on using the negative, you'll get negative 360, which again is the same thing as 0. So anyway you look at it, it's just 0, right? Fine. All right. So now we're going to do the same thing with pi, radians, that is. And just a quick reminder, something you should never forget, pi radians equals 180 degrees. Know that you'll never have a problem. So 3 pi, and by the way, let's just take a quick look at what this implies for our graph. To go in the case of degrees, we know that this is 90. This is another 90, which means a total of 180, 270, and 360. Now, in terms of radians, that implies that this is pi over 2, another pi over 2, which means going to the other side, in other words, landing on that horizontal axis, is a total of pi. Then we have pi over 2 again, pi over 2. So you can label these axes pi over 2, pi, 3 pi over 2. And over here, you could write this as either 2 pi or 0. That tells me how far I've traveled from the origin or the horizontal axis to get to that point. Whereas here, it would be 0 or 360, 90, 180, and 270. So you can see the correspondence between the two. Therefore, 3 pi, now, by the way, if you notice, 3 pi is more than 2 pi. 2 pi means all the way around the circle. So 3 pi means we went all the way around, and then another pi, which means, which is the equivalent. Let's think about it this way. Oh. So pi, let's do it this way. Three pi is actually 540 degrees. So if we're dealing with degrees, we know that that means we've gone around this entire circle once, and then we've gone beyond that all the way into the horizontal axis on the other side. So that means that in terms of radians, 3 pi and pi mean the same thing. Okay. So therefore, the reference angle in this quadrant is, if you're thinking in terms of radians, angle appears pi minus angle. Zero. Okay. So as long as we're actually on the horizontal axis, the reference angle is just 0. If you use the formula from the third quadrant, is the second quadrant formula. The third quadrant formula is angle minus pi. Same thing. It's angle pi minus pi equals 0. So the answer to this question is 0. 0 radians, actually. But it's the same thing as 0 degrees. Anyway, then equivalently 4/3 pi. So, if these confuse you, these radians, you might want to think about just multiplying or converting them into degrees, because that might help you visualize what's happening. And of course, for these types of questions, really the only thing that matters is what quadrant are we in. So 240, so means you've gone, think of this as pi over 2, pi, 3 pi over 2, which is the same as 90, 180, 270. So that means to go through 240 or 4/3 pi, we must have gone through the first two quadrants and then another 60 degrees into the third quadrant. Okay. So this is equivalent. So in other words, 4/3 pi is the same thing as 240 degrees. Now that puts us in the third quadrant, and using radians, the formula here is angle minus pi. Now, here's what you might want to think about doing though. If you're going to use radians, if I put, well, actually, no, it's fine the way it is because all you have to do now is this. Pi over 3. And of course, if you remember, pi over 3 is the same thing as 60 degrees. So you can write the answer as pi over 3. Okay. Great. Now, how about C, 7/6? All right. So again, if you find radians confusing, you could do this. This is equivalent to 210 degrees, which means you went around through the first two quadrants and then an additional 30 degrees into the third quadrant. Oh, wait a minute. Sorry. I just accidentally erased everything I was doing. All right, here we go. So that means what we're looking for is this. Oops, jeez, I did it again. Yeah, there we go. All right, 180 plus 30. In terms of pi, radians, we've got so 7/6 pi is halfway, well, it's part of the way between pi and 3 pi over 2. So that means that when we use the formula, angle minus pi, we'll have 7 pi over 6 minus pi, which is pi over 6, which is the same thing as 30 degrees. So again, if the picture should be helpful, I'm thinking, because again, remember, all this is saying is that once we reach this point, you'd need to go back 30 degrees or pi over 6 radians to get back to the horizontal axis. And then finally, D, 7 pi over 4. And in terms of degrees, that would be the equivalent of what is that the equivalent of? Hold on. Let me just make sure. 7 times 180 divided by 4 is 315. All right, so where do we find that? So we're looking at well, actually, sorry, I didn't draw that very well. Okay, so in terms of degrees, you're going through the first three quadrants and halfway into the
I'm so tired.
so anyway, that is equivalent of 7 pi over 4, Okay, which is exactly halfway between 3/2 pi and 2 pi. So therefore, we're in the fourth quadrant, and then the angle or the formula for the fourth quadrant is 2 pi minus the angle. So that means 2 pi minus 7 pi over 4. Now, of course, 2 pi is the same as 8 pi over 4. And that's pi over 4, which is 45 degrees. So that's exactly what we would have expected. All right. Now, for the rest of these, we're pretty much using either some combination of the calculators and the unit circle chart, combined with our knowledge of the relationships between the different trig functions. And we'll need them all. Okay, so just a quick reminder. Tangent is the sine over the cosine. Cotangent is the inverse. The secant is simply 1 over the cosine. And the cosecant is 1 over the sine. We're going to need all of these sooner or later in the next batch of problems. Okay. Let me just see if we'll need it here. Looks like we're going. Oh, maybe not everyone. There we go. Now we're good. All right. Get this out of the way. All right. So anyway, what do I mean by that? So let's start with tangent pi over 3. Now, luckily, your calculator does have the tangent button, but first things first. If you're going to use your calculator, you've got to make sure that you're in the right mode. Okay. Otherwise, you're going to get the wrong answers. It's a done deal. You can't get the right answer if you're in the wrong mode. All right. So in the TI-84, you just hit the mode button. And if you scroll down a bit and you look at all those modes it has, you'll see that 1, 2, 3, the fourth from the top offers you the option to be in radians mode or degrees mode. If you're not in the right mode, shift over there with your arrow keys and then hit enter. You've got to be in the radians mode for this. Then once you've done that, the way it works is tan. And on this calculator, to get to the pi button, you have to hit second, and then it's directly above the exponentiation key. And then that, in this case, has to be divided by 3. All right, let's try that. The tangent of pi, oops, hold on, divided by 3, it comes out as 1.732. Now, clearly, this is some kind of a radical. We know that because when you look at the unit circle, you'll see that all of these radicals are either radical 2 or radical 3. That's all that we have here. So if you'd rather do this with the unit circle, what you have to do is go to pi over 3, which is here. And you'll notice that according to this, the cosine of 30, not 30, sorry, pi over 3. Oh, I think I'm looking at the wrong one. Wait a minute, hold on. Yes, I am. Hold on a second. Sorry about that. No, pi over 3 is this one. That's better. Okay, great. So for pi over 3, according to this unit circle, the cosine is the x-coordinate, which is 1 over 1/2. The sine is radical 3 over 2. Great. Now, how does that help? Because the tangent, as we saw earlier, can be rewritten as the sine over the cosine, meaning radical 3 over 2 over 1/2, or radical 3 over 2 times 2 over 1, which is radical 3. So this number is an approximation of radical 3. So you can decide which one makes the most sense. You can go directly to the calculator, but that only works for sine, cosine, and tangent, by the way. If you need cosecant or one of the other two, you're going to need to do something like this anyway, where you're redefining it in terms of the other basic trig functions. Okay, so that's that one. Now we have B, the secant of pi over 3. So the secant is the inverse of the cosine. Now, we just got through showing up here that the cosine of pi over 3 is 1/2. So you've got 1 over 1 over 1/2, which is just 2. Okay. And that one is, quite straightforward. They're not all going to be that straightforward. There's a few in here that are actually kind of messy, right? So let's keep going. C is cosecant pi over 3. Now, again, because, we don't have a cosecant button, it's not on the unit circle. We have to remember that this is 1 over the sine. And we just looked it up a minute ago, and we saw that the sine of pi over 3 is radical 3 over 2, which means 2 over radical 3. Now, by convention, we do not want to have a radical in the denominator. So we engage in a process called rationalizing the denominator. In other words, turning it into a rational number. And that means what we're going to do is multiply this by radical 3 over radical 3, which is 2 radical 3 over 3. All right. So that takes care of that one. Now we need D, which is cotangent pi over 3. So we already know that it's simply the inverse of A, but let's just work through the steps. This is the equivalent of cosine pi over 3 divided by the sine of pi over 3. And again, we looked these up earlier. The cosine of pi over 3 is 1/2. And the sine is radical 3 over 2. All right, let's see what we can do with this one. Remember, this is equivalent to multiplying by 2 over radical 3. So drop out. We have 1 over radical 3. And then we want to rationalize that. And that's it. We're done. All right. Well, now we've got some more. These are the ones that are definitely not on your calculator. For example, the cotangent of 30. So remember, it's 1 over the tangent, but that means in turn that it's the cosine over the sine of 30. All right. So we'll go look these up in the unit circle chart. So let's go find 30 degrees, which is this one. The first coordinate is the cosine, of course. The second is the sine. So that means the cosine is radical 3 over 2. The sine is 1/2. So the ratio is radical 3 over 2 over 1/2. And that was just fairly simple. It's just radical 3. Right? We don't have to do anything else with it. Okay. That's an unusual case. You'll see a lot of the others. We do need to do some more algebra when we're done. All right, what else do we have here? B, cosecant 30, which is 1 over the sine, which is 1 over 1/2, which is just 2. Okay, another nice straightforward one. We like straightforward answers, don't we? Yes, we do. Okay, great. Now, how about C? Secant 30 degrees equals 1 over the cosine. And that means 1 over, oh, there it is, radical 3 over 2. Oh, wait, sorry, it's 1 over radical 3 over 2, which is equivalent to 2 over radical 3. And now, of course, I have no idea why that happened. Yeah, the tablet is pretty cool, but it can have its quirky moments. So once again, we rationalize. Oh, actually, sorry, we don't want to cancel anything. It's 2 radical 3 over 3, right? Whatever that is. And in the MindTap assignments, I'm not sure if it's looking for the radicals or the decimals. I guess that depends on the problem. It'll have to tell you. All right. And then finally D. Oh, no, there's more. D is the cotangent of 60. All right. So we looked these up, I think. Let's go get them back from here. So cosine of 60 is 1/2. Just write that down somewhere. And then the sine from the same diagram would be radical 3 over 2. Okay. All right. So then we just need the ratio 1/2 over uh, radical 3 over 2. Let's move that down here. One over radical 3, but then we have to rationalize the denominator. We end up ultimately with radical 3 over 3. All right, beautiful. Let's see what E is. Cosecant 60, which is 1 over the sine. And we just looked this one up. The sine of 60 is radical 3 over 2, which means 2 over radical 3, which we then have to rationalize, and we end up with 2 radical 3 over 3. Great. Then we have, I think there's one more, F. Oh yeah, secant 60. Great. 1 over cosine 60. And from up here, we saw that that's 1/1/2, which means it's just simply 2. Beautiful. Yeah, we like these nice ones. Okay. Now these number 17, which is the end of this document, by the way, these are a little bit messier because we have ratios. So that means we're going to use our definitions, but we have to be careful with them. So for example, A, cosecant 30 over sine 30. Well, what we have to remind ourselves is that cosecant is 1 over the sine. So what we actually have here is 1 over the square of sine 30. This is how it's written, by the way. Sine squared 30 means you're multiplying sine 30 by itself. Now, sine 30 is 1/2. Okay. So this one ends up being 4. Okay. And that's not, it's a nice round number. I like that. Then we have, let's see, part B. Secant 30 over tangent 30. Now we can rewrite both of these. We might get some cancellations if we're lucky. Oh, sorry, what am I doing? It's not 1 over cosine, it's 1 over cosine. Down here we have sine over cosine. Yeah. So when we rewrite that, we can rewrite this as the product of 1 over cosine 30 times cosine 30 over sine 30. Oh, yes, go ahead, Nikoi. Oh, it's okay. You can watch the video to see what you missed so far. Plus, I'll be posting all these answers later on. Okay. So yeah, you missed some stuff, but it's, like I said, you can watch the video if you want. And also all this work that I'm doing here, I'll be saving it and posting it on Brightspace. It's, mostly just trig stuff. It won't be too difficult. But yeah, you got to keep an eye on that old laptop. It always runs out at the worst possible time, doesn't it? It's like your phone. When does the phone run out? Oops, when you really need it. So anyway, the sine of 30, again, we can take it from here as 1/2. And that's just 2. Okay. Beautiful. All right. Now, C. Now, by the way, when I wrote the second midterm, I don't remember how much of it is based on trig, but I think it's not a huge percentage. Because, I think chapter 3 is more important, but you don't want to neglect the trig either because you'll see it all the time in Calc 1 and 2. So we have the sine 30 over the cosine 30. So again, we'll go look these up. 1/2 over radical 3 over 2. Drop out. I have 1 over radical 3, which I can then rationalize. All right, radical 3 over 3. Now, by the way, here's an interesting twist. This is equivalent the tangent of 30. You could actually just go look that up on your calculator. The only thing with that is that you're not going to get radical 3 over 3. You're just going to get the numerical equivalent of it. So in fact, I'm going to do that right now. Tangent 30 is equal to, oops, I just realized I'm in the wrong mode. All right, let me try that again. Tangent 30. It's approximately 0.57735. And if you calculate the ratio of radical 3 over 3, you'll see that that's exactly the same number. Okay. All right. Anyway, and finally, one more. Cotangent 30 over tangent 30. So this is the cosine of 30 over the sine of 30 divided by the sine of 30 over the cosine of 30. So if you rewrite that as the product of the denominator, inverse of the denominator, unfortunately, there's no cancellation. Instead, what you end up with is cosine squared 30 over sine squared 30. All right, so the cosine of 30 is radical 3 over 2. What you've actually got here is radical 3 over 2 squared, and then the sine would be the sine squared. The sine is a half, so we square that. And you end up with 3. All right, so at long last, we're done reviewing. Okay. Now, again, I can't guarantee that any of these questions are actually going to be on your test, but oh God. Well, anyway, yeah, I've got to, the thing about writing on here with the tablets, you got to be careful because if you're not, the writing can get all sort of smushed together and get very sloppy. So I will save this and stop fooling with it while it still looks good. All right, so now we can focus all of our attention on matrix algebra. So I'm going to quickly run through a quick review of it, what we've done up to this point, and then we're going to move ahead into something a little bit more complicated. But it's been a while, so I would like to quickly review the basic concepts, which we did some of them last time, maybe not all of them. So let's see. If you go back to chapter, let's see, this is 8.2. Yeah, we'll start here. 8.1, remember, they were just showing us how to do, how to solve simultaneous equations with the method of substitution and then the back substitution. Here, we just want to remember what matrices are all about. So a matrix is essentially an object that contains rows and columns of numbers. And we uniquely characterize a matrix by its dimensions. Okay, so normally these are used to help us solve simultaneous equations. That's really what the point is, but in a more compact and convenient way than doing it directly. So let's say we have matrix A. It's not 1, 3, 2, 1. All right. So in other words, these elements, we don't know what the actual numerical values are, but what they tell us is the row and the column in which this element is found. So for example, this one in the bottom left-hand corner, A21, means that that's the second row and the first column. This one up here means the first row and the second column. The dimensions of this matrix are written as row times R times C, row times columns. And in this particular example that I'm showing you, it would be 2 by 2. Okay, 2 rows, 2 columns. You would write that as 2 by 2. Always remember rows comes first and columns come second. So then of course, we're going to use actual numbers, but this is in general how we would write a 2 by 2 matrix, 2 rows, 2 columns. And now there's some special cases you may run into. Oh, and by the way, if the number of rows and columns are equal, the matrix is said to be square for obvious reasons. So a square matrix means that it has the same number of rows and columns. Now, the relevance of that is that some matrix operations are only defined for square matrices. So in other words, those are the cases where you must have a square matrix, otherwise you cannot get the results you're looking for. We also have a couple of other special cases, actually three. If we have, let's say, something like this, then this one has dimensions 1 by 3 because there's 1 row and 3 columns. Then B is said to be a row vector, or sometimes it's called a row matrix. And then you have another type of vector when we have only 1 column. So it has dimensions 3 by 1, 3 rows, 1 column, and we call this a column vector or column matrix. And then the final special case that we looked at is this one. It's a matrix with a single element. So this one is called a scalar. It plays the same role in matrix algebra as a constant does in the real number system, where the advantage of this is that I can easily multiply a matrix by any scalar. Okay, but before we get to that, let's remind ourselves what operations we know on matrices we have so far. Well, we defined the concept of equality. That's pretty straightforward. Adding and subtracting. Matrices can be added or subtracted. Font a little bit bigger here than 12. That's better. Okay. Only if they have the same dimensions. All right, so let me give you a quick example of this. I can add these together because they're both 2 by 2. So I'm going to create a new matrix, A plus B. Now, how does that work? Well, if you write A in its more formal way, but this applies to any 2 by 2 matrix. Resulting matrix A plus B is obtained by simply adding these elements together. In other words, I'm adding this number to this one to this one, et cetera, et cetera. In other words, we call that element by element. So the terms, elements of the matrices, are added element by element. It's called. In other words, we only combine elements with the same uh, indices. In other words, the same row and column. All right, so if I go back to this and do the actual numerical example, you'll see what I mean. A plus B would therefore be 1 plus 0, 2 plus 1 is over here, 0 plus minus 1, and then finally 3 plus 2. And that's going to leave me with 1, 3, -1, 5. And that's all there is to it. Okay, and of course, I could also do the same thing with subtraction. This time I'd be subtracting instead of adding, but it's the same basic setup. So matrix addition or multiplication, matrix addition and subtraction is easy, but the matrices have to have the same dimensions. Another thing we can do easily with matrices is scalar. It's called scalar multiplication. So with scalar multiplication, each element of a matrix is multiplied by the scalar. All right, what do we mean by that? So imagine that we have scalar C, and it's 3. So A, if you recall, is what do we have here? 1203. In order to multiply them together, here's all I would have to do. And then I can write that out as 3 times 1, 3 times 2, 3 times 0, and 3 times 3. And that means, of course, 3609 is my final result. All right. Well, now those are the easy ones. So we can either add or subtract matrices as long as they have the right dimensions. And then we can also use scalar multiplication. And by the way, this always works. This does not depend. Does not depend on the size of matrix A or the dimension. All right. Now, the one that we're going to start with today, and we're going to probably spend the rest of the class doing this, is what do you do when you have two matrices that you want to multiply together, but neither one of them is a scalar? Then the rules are a little bit tricky. So yeah, it's going to take a while to go through this, and we're going to come up with some nice examples just to make sure that it makes sense. Also, I think we may have touched on these properties. You can see these are the algebraic properties of matrices and scalars. There's nothing surprising here. This one here, by the way, is a matrix that only contains ones that have the same dimensions as A. But anyway, let's start looking at matrix multiplication. So here's how you have to think about it. So I think we may have mentioned this part. Before you do anything else with matrix multiplication, you have to make sure that the operation is defined. So here in their example, they've got A times B, where A has dimensions m times n, or m by n, and B is n by p. So you notice how they're telling us that these two are equal to each other. So in order to multiply two matrices together, It must be the case that there's two things. Oh, actually, no, it's just the one thing. Um, the columns in the first matrix, or the number of columns, I should say, match the number of rows in the second matrix. And you notice here, that's exactly what happened. If this is true, the resulting matrix will have the same number of rows of the first matrix, the same number of columns of the second matrix. And you can see here what they're telling us in this little diagram is that once we've established that A and B are, we can multiply them out, that means the result here is M by P. Okay, so that's how this works. So it's a little messy. We'll get used to it pretty quickly. Now, there's a point of terminology here. When two matrices, first of all, when two matrices do not have the right do not have the right dimensions to be multiplied, then the product of the two matrices is undefined. Okay? But if the dimensions are correct, like they were here, then we say that A and B are conformable multiplication. Okay. In other words, they can be multiplied. That's all it is. Like here, that was the case. So here, A and B are conformable for multiplication. All right. So now here's the big question. How exactly does one go about multiplying matrices? So here's a good example. We're going to follow their example. Actually, no, I'll tell you what. Let's not use their example. Let's make up a new one so that we can save this for when we get back together on Monday. We'll save that one. I'd like to show you what I think is maybe a simpler case. Suppose A is the matrix 1, 0, 2, 1. B is the matrix 2, 1, 0, 3. Now they're both 2 by 2. So you can see that they're conformable for multiplication. We can multiply them together because those match, and the resulting AB also have dimensions. By the way, I'm going to write these as AB11, AB12, AB21, AB22. You notice that this matrix is also 2 by 2 because we get the number of rows from the first matrix and the number of columns from the second matrix. All right. Now I'm going to show you a very general expression for doing this. And then we'll do some actual numbers. So I'm going to multiply them together. How do I do that? So the first element is going to be, I'm going to call it AB11, so that I know that this is the product that we find in the first row and first column. So I don't think I have enough room to do it like this. Hold on one second. This is going to take up a lot of room. So AB, I'll write it like this. And I mean, so this is with the 2 by 2. Later on, we'll see some really messy cases. So in the upper left-hand corner, because this is AB 1, what we're going to do is multiply the first row of A by the first column of matrix B. And so in other words, I'm taking the first row here and multiplying by this first column. So I'm going to have A11 times B11 plus A12 times B21. Now we'll do the numerical example in a second. And you can see what I mean. There's no way I have enough room to do this properly. So let's see what I can do. Then, all right, I think I can fit this over here. AB12 would be the row 1 of column A, matrix A, times column 2 of B. Okay, and that's going to be, let's look at these together. First row, but now by the second column. So it's going to be, oh my God, let me see if I can make this smaller. I would like it all to be organized as well as possible. So what am I doing again? The first row, A1, is multiplied by the first column, A1 times B11. Then we have A12, which is multiplied by B21. Now, in this case, I'm using the first row of A, but now the second row of B. So you're going to have A11 times B12, okay, meaning these two. And then I'll have A12 times B22. Just barely squeezed it in there. Now, that's just the first two. Now we need to go to AB21. Okay, well, oh God, hold on. I think we can just about fit it in there now. This one is going to be A, the first row again. No, sorry. Now it's the second row of A times the first row of B. So it's A21 times B11 plus, actually, I'll tell you what, I think I'd like to add one more detail here. Just to be consistent, this is going to be row 2 of A times column 1 of B. And the one over here will be row 2 of A times column 2 of B. So this will be A21 times B11, A22. And then in the bottom right hand corner, and again, when you do one with numbers, it'll make infinitely more sense. Let me tell you. So you're going to have A21 times B12 plus A22, B22. All right, so let's go get the actual matrices that we're working with earlier. And we'll see finally how this works. Here we go. All right, it doesn't want to copy. I'll just do it myself. All right. So once again, A is 1021. B is 2103. So we know that they're compatible or conformable rather. So how do we get this done? All right, here we go. We know that this is going to be a 2 by 2 matrix, so we're multiplying the first row by the first column. 1 times 2 plus 0 times 0 is the first element. The second one will be the first row times the second column, which is 1 times 1 plus 0 times 3. All right. Then down here, AB21 is the second row in the first column. And then finally down here we have AB22. Now we're multiplying the second row of A by the second column of B. So that's 2 times 1 plus 1 times 3. Now we just have to do the algebra. So in the upper left-hand corner, we have 2 plus 0. Upper right-hand corner, 1 plus 0. Bottom left-hand corner, 4 plus 0. Bottom right-hand corner, 2 plus 3. And that's our final result. Now that was a lot of work, wasn't it? It sure was. It looks very scary, but believe me, after you've done 2 or 3 of these, or well, all right, maybe more than that, but you'll get the hang of it very quickly. It looks a lot more intimidating than it really is. All of them were conducted before COVID, and also one of them was 2013, and there. All right. Now, I would like to show you, though, a little fun side note, which is that Excel can actually do this. If you're familiar with Excel, it really is a very powerful package. And I would just like to quickly show you how you could actually implement matrix multiplication in Excel. So here's what you would have to do. So let's try this example again and just confirm it. A is, so here's how I'm going to show this. I think it'll be easiest if I do it like this. I'd like to show where the matrices are. So the first one is 1021. Oh, wait, I see you have a question. Oh, all right. It hardly matters because you can watch the recording after we're done. It's okay. I know, the internet is spotty in some parts of the campus. So, or actually the internet is spotty in lots of parts of the world for that matter. But so if you missed what we were doing, I'll not only be posting the video, but all these documents that I'm working on, there'll be copies on Brightspace so you can go through and see what you missed. Okay. All right. Anyway, so this is A. So just to make sure it's clear, I'm going to highlight that. And then for B, to make sure I didn't make a mistake, 1021. Good. B, 2103. And let's say I'll make this one green. I want it to be clear that these are matrices. That's why I'm doing this. All right, so this is A. And if you notice, the dimensions are 2 by 2. This is B, and its dimensions are 2 by 2. So we know that they can be multiplied together. The result will also be 2 by 2. We'll call it AB. And we want to know, let's make this orange, I guess. What is the product of these two? So here's how you do this in Excel. The command is called mmult, and it wants to know where are the first and second matrices. Now, here's the tricky part. Instead of hitting enter like you normally do with Excel, you have to hit 3 keys at once. Uh-oh, see, now I goofed it up. Hold on. You have to select all the cells, which I obviously forgot to do. And the tricky part, which makes it different from other commands in Excel, is you have to hit Shift Control Enter. Okay, so after typing in a mult command, you must hit Shift Control Enter, or whatever the Mac equivalent is, simultaneously, all at once, that is, to get a result. Okay, now you may want to use this to double check your results. Or maybe you don't want to do this at all. But I mean, I just want you to know that it's here. And if you notice, it's 2145, which is what we got. So we must have done it correctly. Excel agrees with us. Okay, so I, in principle, can multiply any matrices I want using Excel. Now, it's also possible that Symbolab can do this, although I've not investigated that. But at least if you're an Excel user, you might be tempted to use this as at least a way of double checking your results. Because you can see Excel can do so many different things. Anyway, what I did with the other classes, I just basically gave them several examples of this. Because like I said, it's going to take a while to get used to this. So I'd like to stick with these simple 2x2 cases. Later on, we can try the more complicated ones. Oh, let's change. Wait a minute. I don't want 2 zeros there. That'll. Let's try -2. All right. So we know these are both 2x2. There, we can multiply them together. AB will have dimensions 2x2. But how do we obtain AB? So the first element, which we call AB11, is the first row of A times the first column of B, which is these two. 1 times 1, 3 times 0. AB12 is the first row of A times column 2 of B. You can tell by the subscripts, by the way, what you're doing here. And that's going to be first row by the second column, 1 times 2, 3 times -2. Now, in the bottom left-hand corner, this is AB21. This is row 2 of A times column 1 of B, which means this row and this column here. 0 times 1, -1 times 0. And then finally down here in the bottom left-hand corner, row 2 of A, column 2 of B. Or in other words, now we're looking at the second row and the second column. 0 times 2, -1 times -2. That's the challenging part, lining them up correctly and multiplying the correct rows and columns together. The rest of this is easy. You're just literally multiplying all these out, adding them up. Okay, so we're going to wind up ultimately with upper left-hand corner, AB11 is 1 plus 0. Upper right-hand corner, 2 plus 2 minus 6. Bottom left-hand corner is just 0, and the bottom right-hand corner is 2. All right, so let's see if Excel agrees with us. All right, so what do we have here? 130 -1. Over here for B, we have 120 -2. So once again, I'll make this yellow, green. Oops, that's not what I meant to do. And I'll make these orange because I don't know what the answers are yet. And again, this is A 2 by 2, B 2 by 2. AB is also, in this case, 2 by 2. So here's, again, we select the whole thing, equals M mult. By the way, Excel calls them arrays, as opposed to matrices. Array is a more general term, but it means the same thing. So once again, Shift Control Enter. So did we do it right? 1 -402. Here we are. Must have done it right. How do you like that? Wow. So now what is going to follow after this is we're going to change the dimensions to make it a little bit more challenging. Okay. But I think that might have to be enough for now because, you know, when we come back on Monday, we'll go back and revisit these examples. We'll work on them on the board and then we'll try some more complicated cases. So after this, we're going to look at an operation which takes the place of division in matrix algebra, and that will also be somewhat complicated. After that, it won't be very difficult at all. The rest is a lot of definitions, and then we're going to see how we can use matrix algebra to solve for simultaneous equations, which is, of course, ultimately our main goal. So I think we've had enough for one day. So why don't we stop here, and I'll post all this good stuff on Brightspace, including the videos, and also on my YouTube account, we'll have the videos. And then you can just go through and look at it anytime you need to. You can review, you can refresh your memory. If you couldn't make it, you can watch it separately. So unless something bizarre happens again, I'll see you in the classroom on Monday. Okay?
All right, Professor.
All right, see you next time.
Thank you.
Thank
All right,
you.
bye. See you later.
Thank you.
All right, bye. See you later.